Professor Ranjani Viswanatha, who is a professor in the Jawaharlal Nehru Center for Advanced Scientific Research. Her area is quantum dots, and her work has been recognized by numerous national awards and recognitions in India, and she serves on the editorial advisory boards and reviews for numerous leading journals in her area, and she's going to tell us about her work on the energy efficiency through manganese doping in perovskite materials. So, welcome.
Thank you, Bilgu, for the introduction. And at the outset, I would like to thank all the organizers for bringing me here and giving me this opportunity to present some of my work here. And I've enjoyed many of the talks so far, and it's a wonderful opportunity to see forward. So today I'm going to talk about the hidden glow, where I say it's unlocking light with manganese and perovskites. So when I say about hidden glow, what I mean is basically I'm going to look at the mechanism of manganese emission in perovskite halides. And I belong to the Jawaharlal Nehru Center for Advanced Scientific Research, and I've been a professor there for the last several years. Okay, before I get started, I'm just the face of this. This work has been driven by my students. Specifically, it was started, Specifically, it was started by my student Pradeep, who has since graduated and is currently in Northwestern University. It's taken forward by Shubham, who is almost about to graduate in this coming year, and a very smart master student, Shudipa, along with Prasanjit helping them. And we have also had a number of collaborators in various regions, and I would like to thank the funding agencies. And this work was also supported by the Sheikh Sakar Laboratory. And this is my lab in 2023. We have a more recent photo, but I haven't put it up, the 2024-25 photo. But this is my lab in 2024. Okay, so when we talk about energy efficiency in perovskites, perovskites have greatly shown a lot of promise with in optoelectronic devices, photovoltaics, like quantum, the lasing, LEDs, photovoltaics, so on and so forth. But however, there is a lot of parameters to be understood. For example, stability, photophysics, structural diversity, dimensionality. A large number of them play a very important role. And enhancing light emission is key to their applications. They are not normally in the phase where we can enhance. They've so far not really reached to the phase of where we can enhance this, use them for applications. So when I talk about energy efficiency, what are the key challenges? The key challenges are, for example, the stability challenges. For example, you may have all heard about moisture sensitivity, thermal instability, UV degradation, and so on and so forth. In addition, perovskites have the unique structure, bonding, and structural issues. They're all ionic bonds. So a small amount of energy is enough to create structural distortions, and dimensionality can create a large number of issues. There are several energy loss mechanisms. There's the non-radiative recombination, hot carrier thermalization, and of course there are the scalability and manufacturing issues, which I'm not going to get into. So the question is, the origin of all of these have been really beaten to death. The role of perovskite crystal structure, dimensionality, structure, electronic structure, device architecture, you talk about it and it has been extensively discussed in literature. So where are the loopholes and what do we present here? So that's the talk of today's talk. That's the topic of today's talk. So how do we reduce non-radiative loss and increase the range of absorption with optimum cross-section? So in this area, the one thing that has played a big role so far in 2,6 semiconductors and has been slowly taken over into the perovskites is doping in transition metal ions. So when I look at transition metal ions, we are talking of large Stokes shift, which minimizes self-absorption, higher excited state lifetime because manganese has a forbidden transition, thermal environmental robustness, and a long PL, so on and so forth. When it was transferred on to the perovskite, yes, true, it did give you some very similar results in cesium lead chloride, but at the same time, there were a huge number of anomalous observations in the manganese doped perovskites, specifically in the area of cesium lead bromide and similar systems. When I say anomalous effects, what do I mean? So the first thing that people observed is this 2.1 EV peak, which has been attributed to the DD transition of the transition metal ion, has been used as a signature for all of the manganese efficient incorporation of the manganese. And the absence of this peak in this cesium lead bromide structures, so the lack of manganese emission is actually what was initially anomalous. It was initially thought that manganese is not effectively doped to the nanocrystals, but we have since shown that if you look at the slow, only the slow component, then manganese is indeed there, but it's not showing this signature manganese emission peak. And in order to understand this, what we did was we looked at first the lifetime. When you look at the long-lived excitonic lifetime, you see that it matches very well with the manganese. So the orange one here is the manganese emission, and the blue one here, there's a very fast decay component and followed by a very long-lived component. So suggesting that there is, and this is in the excitonic emission, this is not the manganese emission. The orange one is the manganese emission, and the blue one is the excitonic emission. So the lifetime of manganese dope sample at the band edge has a very long-lived component. It's very small, but small as in like there is a component which is fastly decaying very fast, but there is this long-lived component, and that matches exactly with the lifetime of the manganese. So we said like, okay, since it's very small and it tends to get buried inside with the fast component, let us look at the gated emission. When I say gated emission, what I mean is basically I'm going to ignore all the fast component, the first few nanoseconds, first few microseconds, and then I'm going to collect steady state emission across the entire spectrum, and this is known as the gated emission because I'm going to insert a gate and then collect the rest of them. So when I did a gated emission, we found something very interesting. So when people have earlier done gated emission, they expected the manganese emission almost very similar to this because manganese is millisecond long lived, and I expect after a few microseconds manganese was there. But what is interesting is not just this peak is there all throughout, and that's not surprising, but the band edge emission, presence of band edge emission in gated PL. This suggests that band edge emission is extremely long-lived. Typically in undoped systems, they tend to decay within a few nanoseconds, and they have no business to be here in a few microseconds time. So this suggests that there is a strong coupling of the manganese with the band edge emission, and it's also very sensitive to which compound that you're using. For example, in the chloride setup, you do not have it, but in the bromide setup, it is very, very strong. So this led us to the point that probably we have vibrationally assisted delayed fluorescence, similar to the lines of thermally assisted delayed fluorescence, but it is a little different than the thermally assisted delayed fluorescence. I'll come to that if in the later slides. So what do I mean by vibrationally assisted delayed fluorescence? It's basically an energy transfer and a back transfer. So you have an excited electron that transfer energy to the manganese dopant, which is non-radiative, and the manganese energy states interact with the host through vibrational coupling, and finally the energy is drift fed back to the conduction band. So what is the role of vibrational coupling? Here there is phonon interactions that assist electron transfer and enhance the charge carrier recombination pathways. So if this is true, what is the impact on emission? So it leads to long-lived excitonic emission and enhances the overall quantum yield, reduces the non-radiative pathways. So in a nutshell, if I were to summarize this in pictorially, so what I mean is, as soon as I observe, excite a few photoelectrons, instead of going through this path, which is the normal path, the manganese level comes in and picks it up very quickly. And normally it would just emit in its own time. But with vibrational coupling, it does not emit through the manganese lifetime, but it couples back specifically to the radiative channels of the host and deprives it of the non-radiative channels. So this is very interesting because basically what I'm talking of is like a storage of electrons inside the manganese, and as and when it recombines radiatively, I'm going to provide a few more electrons. So can it be possible? And if so, why? What is our understanding of this VADF? So we did some basic density functional theory calculations, and the ones that's shown here is very interesting. The red line here is the manganese. The green line is the host, and you can see that I have used this color code. The manganese is red, bromine is blue, and green is lead dominant states. So anything in between, like orange, is basically a mixture of these two states. So you see here that basically normally what happens is the manganese levels are at the bottom of the conduction band here. But in these nanocrystals, cesium lead bromide, the conduction band, because of the spin orbit coupling, is pulled down much more lower, which means the manganese emission is actually buried deep into the nanocrystals. And because it's buried deep, it has chances of interacting through vibrational states. And does it actually interact? So for that, we looked at the phonon band structure, and you see that at the gamma point, specifically for the cesium lead bromide, you see that instead of having just blue, green, or red as I should be, there is a whole range of colors over here, suggesting that there is a strong interaction. The same is true for chloride, but a much weaker. You can see just a small light blue instead of a whole range of colors. So basically, there is strong vibrational coupling for the manganese doping in cesium lead bromide, weak coupling in manganese doped cesium lead chloride. So theoretically, we see that it is indeed possible. So experimentally, can we observe this? So what I would do is, if I need to prove that there is basically a phonon interaction, what I need to do is to show that if there is a phonon interaction, it's actually stronger at lower temperatures, unlike TADF, which is thermally assisted, which becomes stronger at higher temperatures. This should become stronger at lower temperatures. And sure enough, you see that if you take a compound which is, when I say 40, I mean 40% chlorine and 60% bromine. So you see that basically at room temperature there is no excitonic emission, and as you go down in temperature, you see that there is this bandage emission. If I were to see across all of the states, I can see here that at a particular state, particular temperature, it starts to go up very strongly, and that is dependent on what is the band gap. And the second thing that I should be observing is, if it is related to phonon coupling, I should be seeing a phonon mode that would arise at this particular temperature and basically follow through with whatever temperature dependence of the PL I'm observing, which is what basically we saw with the Raman temperature dependent Raman features. We saw this feature that is coming up. This is related to the cesium stretch frequency, and we see that it starts to arise around 240 Kelvin for the one which is this, and you can see here that it starts to rise around 240 Kelvin, and then over lower temperatures you see that smudging with the rest of the peak. So basically now we have shown that actually manganese can interact, have a vibrational coupling, and what is the direct proof? Now if this is indeed coupling, I said that emission channels should become more radiative. I should be not losing energy as heat, so which means the quantum yield should increase. So we did see that with increasing manganese doping, you see that the manganese emission of course is going down, but the bandage emission is increasing the radiative pathway from 40% to 60%. So we basically said that okay, fine, we have phonon coupling, and because of which we are seeing an increase in the quantum yield. So now what is the next step? The next step is to figure out where, from what states are these coming in? Are they coming in from the lowest energy states? Are they coming in from the higher excited states? And in order to study that, we wanted to see how we can do that, which states couple. So what we did is, basically what we decided was that we can actually tune the band gap through two means. One of them wherein we are changing the composition, which is what I have been talking about, so that I can say whether it's the lowest excited state or not. And the second one wherein I can modulate the size and still tune the band gap. And if it's the lowest excited state, both of them should show similar results. So this is how we had this. So we have samples which are going from 20% chlorine to all the bromine to 80% bromine. And we took something around 50%, and we said, okay, I'm going to change the band gap by changing the size from 7 nanometers all the way up to 13 nanometers. And you can see that the band gaps are varying in the similar region. So now I wanted to see what is the effect on VADF. So when I look at the effect on the VADF, as a function of composition, I see that the host band gap is coming up at a particular energy onwards. So basically if the band gap is decreasing, I am seeing an increase in the delayed fluorescence. But unlike that, if I were looking at the variation in size, irrespective of what is the band gap, I see the same amount of excitonic band gap, almost no change. So this suggests to me that it is not the lowest energy state, but actually the higher energy states. So when we did look at the origin of these things using PLE, so basically this is how we were observing for variation in the band gap. You see that for composition it changes like these dotted lines, but when I change the size it is one and the same. So what we did was trying to get this mechanism through energy, and we look at the PLE, which is the excitation, which basically gives rise to this delayed emission. So we looked at the gated PLE to see where is this coming from. And to our surprise, we see that for the composition variation, not just the first excited state, but all the second, third, fourth changes. But when I have size variation, the first excited state does change, but the second, third, fourth are more or less at the same position. And since my VADF is not changing as a function of size, we believe that the higher excited states are responsible for coupling this manganese with the host and not the lowest excited states. So if I were to summarize this whole thing into a pictorial representation, so what I am talking of here is basically I have an electron back transfer from manganese to the host in manganese dope CSPB X3 quantum dots through vibrational coupling. So basically with cesium-lead bromide, I have an exact kind of a click chemistry wherein exactly the whole phonon interaction is very well matched and the entire energy is transferred. And for the bromide, it is for the chloride, it is not so well matched, but still matched good enough for me to have the transfer, especially at lower temperatures. And for the 2,6 semiconductors, there is no interaction with the manganese. So now the big question is, I have been talking about this transfer as a charge transfer. I have not specifically, it could very well be an energy transfer as well. So how do I distinguish between the energy transfer and the charge transfer? So in order to distinguish between energy transfer and charge transfer, I had to come up with a new mechanism to confirm this is indeed an electron transfer. So what we did is, since we are studying the electron back transfer, we thought what better way is there to see the Förster resonance. So basically, I am going to have a physical adsorption of more number of a dye, and we know what is the mechanism, like the fret mechanism is very well studied in literature. So if I pair up the cesium lead bromide with rhodamine 6G, if there is an electron to recombine at the band gap, then there will be an energy transfer. If not, there is going to be no energy transfer. And so this is not the first time that has been done. This has been done extensively in literature and pretty well studied. So what people do is, if you just titrate the dye, you see that there is a decrease in the excitonic peak and an increase in the dye peak. So this is like an expanded view where you can see that it is increasing. So now our point of contention was, if manganese is actually doing something to the excitonic feature, then this efficiency should increase. Efficiency of fret transfer should increase, because as you're all well aware, there is no scope for a direct excitation in terms of for the rhodamine 6G at 400 nanometers, which is where we are exciting. So this is basically how we are going to do it. We just want to make sure if there is a vibrational coupling, and then if it is indeed an electron transfer, and then this electron recombines, transfers this energy back to this one, wherein you have an excitation, and then you see an increased R6G emission. If you see an increased R6G emission through the manganese states, then you will, we agree that there is an excited state. These are just normal bookkeeping to make sure that there is a good spectral overlap of the donor and the acceptor, and you can see that R6G is indeed overlapping very strongly, both in case of doped and undoped. So now my question is whether does it change, if the transfer efficiency, does it change as a function of doping or not? So this is what we did. We put in these systems, and very nicely we could see that as you go from cesium lead bromide to manganese doped cesium lead bromide, you could see almost a 4-fold increase in the PL intensity of the dye. And this enhancement is what we claim to be due to the increase in the drip feeding of the charge carriers. And basically another thing which came out as a relatively surprise, this thing, was because it's a drip feeding, meaning once you recombine, only then it gets this energy back. Although it is not Stokes shifted, we do not see an self-absorption at very high intensity as well. So this is even better seen here when you change the ratios of the cesium lead bromide to that of the dye. Instead of titrating with the dye, why not titrate with the bromide efficiency? So we see that it just keeps increasing. You keep adding more and more cesium lead bromide. It's not, normally in most systems, because of self-absorption, it kills itself. But in this case, the self-absorption is significantly reduced and the fret efficiency is increased. So when we tried to do this for different concentrations of manganese, there were 2 or 3 things that came into light. The first thing is, of course, an increase in the efficiency from 26% to 93%. And the referee asked us, how do you know it's not because of the surface interactions? You could have very well surface interactions. So we did add manganese bromide as a control, and we see that nothing changes. And as a function of manganese concentration, you see that it keeps increasing up to about 2%. And very interestingly, by 5% it comes down. That's not very surprising though, because by that time you have a manganese-manganese interaction. We are not interested in manganese-manganese interaction. We are looking at interaction between manganese to the host. So if you have manganese-manganese interactions, then it's going to kill this variation. And you can see here that wherever that efficiency is very high, it also keeps increasing to higher and higher ratios of R6G, suggesting that there is no self-absorption problem. Okay, so finally we also observed that with lifetime, you can see that manganese lifetime is, with increasing addition of R6G, the lifetime of manganese is decreasing. The donor lifetime decreases because there is a recombination through the dye route, but of course there is a lot of parameters including IRF problems, which is resolution of our instrument, because we are going from milliseconds all the way down to few nanoseconds or even picoseconds. So there are a lot of different instruments used, so we could not quantify that. But finally, the last thing that we did is, okay, if fret efficiency is indeed increasing because of this, the last thing that I'm going to do is I'm going to take the chloride system, and the chloride system, as I have been talking about, is not going to be vibrationally coupling with manganese at room temperature. So I should not see an increase in the fret efficiency at room temperature, but when I go to low temperature, I should see an increase, and which is exactly what I observe here. So I see that with increasing at room temperature, whether I have manganese or no manganese, the red and blue are almost overlapping with each other. Whereas when I go down to lower temperature, I see that effects of the similar effects are being observed as I did for at room temperature. And basically this is the black curve is what I am talking about. So I see that when I go down to 77 Kelvin, which is above the fret efficiency limit, then the phonon coupling temperature, below the phonon coupling temperature, I see this fret efficiency increase. If it is above the phonon coupling temperature, then the fret efficiency doesn't change. Okay, so I think I've almost come to the last 10 minutes. So I would like to summarize this talk by looking at the key takeaways for energy harvesting. So manganese doping enhances fret due to charge back transfer, and this is basically what we are talking about is an electron drip feeding. This increases due to charge transfer efficiency, and the drip feeding, because of the fact that it's a drip feeding, also harnesses, gives me the, although there is no Stokes shift, it gives me the opportunity to avoid self-absorption, and because of which it is also tunable. I'm just using the excitonic emission, it's still tunable, and it has potential applications in high performance optoelectronics. And phonon coupling with manganese, the host is a key. We're still working on different systems to see what is special about this particular system. But, and actually the electronic structure of perovskite is a very interesting system. Optical properties of these materials are completely altered, be it the halide or the anion or the cation. You just change one thing, the entire structure changes. In addition, it also has this problem, problem or advantage, I don't know, but because you are taking very small, very weak ionic bonds, any changes are very easy to make. So that's another story for another day. And thank you all for your attention.
Excellent. Thank you so much for this wonderful talk. It's open for questions. So let me ask one question. Could you clarify for me where manganese dopes in this compound? And is it only electronic effect, but does it cause also other charge defects that can compensate for manganese?
So we like to believe that it is doping into the structure of the perovskite, like replacing lead.
Lead.
Uh-huh.
So can it not replace cesium?
I cannot tell you for sure,
Yeah.
but we believe that it should replace lead. Some of the features, like for example, observing this DD transition, suggest that it's not a surface replacement. But the bigger problem is because these are very sensitive in the sense like they're ionic bonds. It's very easy to make and break these bonds. So even as simple, most often I confirm the position from exafs. I look at the surroundings of that and I confirm. But in these cases, we've tried a lot. What happens is the moment I hit it with a beam, it oxidizes. So
And
I'm not able to
that
confirm.
affect also the halide stoichiometry?
Halide stoichiometry is something we could exactly confirm from the exafs. So we could look at the halide peak and the lead peak. If you were to look at the lead K edge transition or the lead L3 edge, you could clearly map it onto two particular paths, CM chloride, lead chloride and the lead bromide. And if you were to take the relative intensity, we could almost within plus minus 3-4%. It was what we had expected stoichiometrically.
So when you dope the lead site with manganese,
it doesn't change. The halide
the
composition
coordination
doesn't
with halide
change.
doesn't change. Okay.
And
So it's all
lead is also
electronic.
2+, manganese is 2+, so we do not expect charge effects.
So manganese can change oxidation state.
Yes, but that would require a lot more energy. These are very, we put them in 2+ state. It's very difficult to break this lead bromide bond or the manganese bromide bond or chloride. It's much easier to, cesium is just there as an ionic bond. The lead bromide and the manganese bromide are much more stronger. So that's why we believe that cesium just rattles in and out in the structure.
Good. Thank you for clarifying. Okay. Any other questions? If not, let's thank our last speaker again.
Thank you.